Hello everyone, I'm Zixuan from Stanford CNS Lab. You can call me Zux either. Today I will present our IPMI work that tries to develop new method to interpret deep classifiers. This work was done with the help of Dr. Zhao Qingyu and advised by Professor Kilian Po when I was a research assistant at the Stanford CNS Lab. Alright, let's start. In recent years, deep learning has achieved great success in medical imaging and neuroimaging community. Deep learning-based methods have achieved state-of-the-art performance on many disease classification tasks. For example, many works have reported more than 90% accuracy on Alzheimer diseases versus control normal classification tasks. The main reason for deep learning success is that they tend to have very complex inner structure. However, these complex structures of deep vision model also bring another great challenge. That is, it's very hard for us to interpret the decision made by these deep classifiers. In computer vision community, one common solution to this problem is to generate meaningful heatmap to notify the importance or contributions of voxels or subregions in the input image. This approach can be defined, actually ill-defined, as a problem called interpret by visualization problem. That is, suppose we have a dataset and a trained classifier using data in this dataset, as well as a learning target called objective. Our target is to design a visualization algorithm that could generate visualization map for each subject in the dataset. The reason why it's ill-defined is that we actually didn't know what is the right way to describe meaningful and learning target. In general, what is meaningful is actually depending on the target we want to seek. For example, someone might say it's meaningful to show the importance of each voxel subregion to the decision. Some might say it's meaningful to show some properties that we are interested, like changing tendency of voxel intensity or shape patterns of some certain regions. There are some prior works tries to develop such visualization algorithm to show the importance of decision made by the classifier of each voxel or subregion of the input image. For example, if we want to evaluate how a classifier decides an image to be a cat, we can generate corresponding heat map to show the importance of each pixel. Or if we want to evaluate the decision consider the image as a dog, we may generate another visualization map. There are two common methods to do so. The first class is called Saliency map-based method, which they try to leverage partial derivatives during backpropagation. And the second class is called alteration map-based method, which they try to iteratively run leave-one-out inference to evaluate the importance of pixel or subregion of input image to the final decision. These methods are widely used in classical image classification visualization tasks and achieved good qualitative performance. However, when directly applying these methods to neuroimaging studies, it turns out that these methods are not that informative. For example, the popular GradCam method tends to give too smooth results and cannot locate precisely to the meaningful region with respect to the disease effect. And the backpropagation method tends to give too noisy results with frequent sign change. And the alteration-based map-based method can only give group-level analysis. It turns out that all these methods cannot inform specific alterations caused by the disease. Thus, it's very important to develop new visualization methods to address this issue. To better visualize the disease alteration or so-called disease pattern captured by the trained classifier, we use this green shape to denote it. Inspired by image-to-image simulation scheme, we proposed to first model the disease alteration process to an image-to-image simulation process with image generation networks and so-called simulator networks here. The simulator networks could generate desired simulated images based on the inference result given by the trained classifier. Then we can generate visualization maps based on the simulator networks. Since both the trained classifier, the simulator networks are all deep vision models, we call this method to train deep model to interpret deep model. Okay, in this framework, The first and the core idea we used is unpaired image-to-image simulation. Suppose we have the raw control image and disease image cohorts, and a trained classifier. Note that for simplicity, we give the control cohort label 0 and give the disease cohort label 1. Here, the PC is larger than PD, means that the classifier considers the blue dot as control, and vice versa for the raw disease red dot. The unpaired image-to-image simulation is to train two simulators, the disease simulator G1 and the control simulator G2, and G1 will transfer the control image to a simulated disease image, and G2 will transfer the disease image to a simulated control image. Equivalently, we can think of the simulators inject or remove the disease pattern in the raw image, while at the same time preserve the subject-specific pattern and at the same time try to fool the classifier using the simulated image. One difficulty here is the unpaired term, which means we actually don't have the paired control and disease view from the same subject at the same time. This is always true in reality, as we know that one people cannot be both healthy and diseased simultaneously. To address this difficulty, we leverage a notion called cycle consistency. The cycle consistency is basically saying that since we cannot get paired view to supervise the simulation networks, we can actually extend the simulation process by further recover the raw input image from the simulated image using the other simulator. This cycle back image should be as much as similar to the raw input as the raw input image in both directions. By this way, we could somehow constrain the simulation process to be invertible and be able to generate valid simulated image. Then, next question is how to help the simulator to generate simulated image that could fool the classifier. Here we propose a novel logic shift loss, which is to enforce the model to generate images that could shift the predicted logic by the classifier by at least a delta larger. For example, let's take the left part as an example. Since the control label is 0, and in this case the logic P before sigmoid is smaller than 0 if the classifier is making right decision, then the disease simulator should generate simulated image with P hat larger than P plus delta, and vice versa for the right part. In this case, P is larger than 0 if making correct decision. The control simulator should generate new image with P hat smaller than P minus delta. This loss helps the simulator to learn how to formulate the disease alteration. We also give a mathematical formulation of the cycle consistency loss, which is to measure the similarity between the raw image and the cycle back image in both directions using L2 norm. Alright, the second core idea in our framework is to couple the two simulators into a unified one using conditional convolution. This is motivated by the observation that these two simulators tries to learn symmetric operations, equivalently, either injecting or removing disease patterns. The idea of conditional convolution is that to use multiple convolution kernels with learnable weights instead of using only one kernel in each convolution layers. The learnable weights can be inferred by a routing function with the specific task ID embedded as a part of the input of the routing function. With this design, we can make the coupling simulators with conditional convolution layer to adjust their behavior based on the specific task ID. The third idea is to leverage the warping field learning scheme. It's a commonly used technique to learn pattern shape changing, which is to learn a 3D deformation field, and then apply linear interpolation to the raw input image based on the learned warping field to get the warped image. Following the voxelmorph paper, we add on a smoothness regularization during training, which is to constrain the gradient norm of each direction in the deformation field. Note that this part is optional and will only be applied based on some specific experimental setting. Okay, next I will present some experimental results. We applied our method on 3 experiments, and the first experiment was conducted on a synthetic image dataset. This dataset has two image cohorts, the control cohort and disease cohort. Each image is composed of a 2x2 subregion panel with a Gaussian signal in each subregion. For the two diagonal subregion boxed by the green square, it denotes subject-specific pattern, which is randomly sampled across the subjects. For two off-diagonal subregion, it denotes the control and disease pattern. For the left figure with off-diagonal region boxed by the blue square, it denotes the control pattern, with a Gaussian signal with lower intensity sampled from an uniform distribution. For the right figure boxed by the red square, it denotes the disease pattern with a Gaussian signal with higher intensity sampled from another uniform distribution with higher expectation value. To apply our method on this dataset, we generate 1024 images with balanced ratio on each cohort and train the classifier with around 88% test accuracy. Then we train simulator networks to model the image simulation process, and note that there is no warping field learning. After that, we generate the corresponding visualization by measuring difference between raw image and simulated image. Here are the example simulation results generated by CountCom simulator. As we can see, the simulator successfully accomplished its task in both directions, i.e., it successfully increased the intensity of Gaussian signal in off-diagonal part of raw control image, and it successfully decreased the intensity of Gaussian signal in off-diagonal part of raw disease image, while at the same time, it preserves intensity of the diagonal part for both directions. To further analyze our results, we generate the corresponding visualization heat map by measuring the difference between raw control and simulated disease image. Note that here we only focus the control to disease simulation. We can then compare our generated visualization with ground truth and other baseline methods. Note that all the visualization maps are normalized to same scale. Here we can see our results with CountCom simulators generates the most similar results to ground truth, while backpropagation, guided BP, guided GradCam generates very noisy results. The GradCam generates two smooth results with two large region location. Also note that without conditional convolution, the simulators generate less informative results, which indicates that conditional convolution is necessary here. We further measure the group level performance of each method by using normalized cross-correlation score to measure the similarity between the generated visualization and ground truth. We can see that our method with CountCom gets best result in both terms of point estimate and confidence interval. Next, we applied our method on a real neural imaging dataset, the ADNI-1 dataset, which contains 1,344 T1 weighted MRIs with 229 normal control subjects and 185 subjects with Alzheimer diseases. And for these two cohorts, their age are matched. We first train a CNN classifier with 88% test accuracy on ADNC classification. Then we train simulator networks with learning warping fields option. For the corresponding subject level visualization generation, we calculate the Jacobian map based on the warping field. And also note that besides the subject level visualization, to generate group level visualization, we first register structural maps of all control subjects to a template and computing the average Jacobian map in the template space. Now, let's take a look on the example subject level simulation results and its corresponding Jacobian map visualizations. As we can see again, the simulator network successfully captured the informative disease pattern. If we look at the left part, we can see the disease simulator gets simulated image with enlarging ventricles and cerebrospinal fluid part, as well as shrinking brain tissue here. And the opposite phenomena happens in the right parts too. These phenomena are consistent with the medical research results that indicates the effect of AD will lead to enlarging ventricle and CSF, as well as shrinking brain tissue. Then let's look at the produced visualization map. It shows the trend of region will either expand or shrink. while blue means expansion, red means shrinkage. We can see in the left part, the ventricle is expanding, and brain tissue is shrinking. And sort of symmetric result is shown in the right part's Jacobian map. This shows that the simulated network successfully learns symmetric simulation process in these two directions. We can then compare the Jacobian map visualizations to other baseline methods. As we can see, in both directions, the baseline method tends to generate either too smooth and less informative result or too noisy result with frequent sign change, while the Jacobian map successfully captures the better disease alteration pattern in both directions. We also generate group-level visualization results for some baseline methods and our methods. We can see that in group level, our method still generates visualization that indicates consistent results with medical research results. Note that here we focus on AD effect on control subject, so we can see enlarging ventricle and CSF region, as well as brain tissue atrophy. We also do an ablation study to check the effectiveness of logic shift loss design. Here, we compared with training framework with simple binary adversarial loss and draw the logic shift of raw disease cohort, simulated control cohort, and the cycleback disease cohort. As we can see, while the logic shift loss could help the simulated networks uncover the pattern that is correlated with severity of brain disorder, as we can see, the logic difference between these three cohorts remains more consistent. The result using binary adversarial loss tends to simply fool the classifier as much as it could. This might lead the simulator to learn undesired pattern. Last but not least, we applied our method on another neuroimaging dataset with 1,225 T1 weighted MRIs, which contains 2,274 normal control subjects and 329 subjects with alcohol use disorder. Note that the ages are matched for each cohort. Similar to experiments before, we trained the CNN classifier with 76% test accuracy on AUD or NC classification. Then we trained the simulator networks and do the group level visualization by similar way we did in ADNI experiments. From the Jacobian map visualization, we can see that the most severity atrophy are located at orbital frontal lobe. This is consistent with the medical research result that disruption in the structural and functional properties of orbital cortex associated with alcohol dependence. We further do a classical group test between raw control cohort and simulated disease cohort on 4 regions of interest to see if the gray matter volume is significantly different in this ROI. With age and gender being covariates, we can see both these 4 ROIs, superior and medial frontal orbital gyri, the rectus, and the olfactory gyrus, have significant difference on gray matter volume. Both of them are shrinking. These results are also consistent to the recent medical research result. In conclusion, we note that in this work, we propose a novel visualization technique with better interpretability via cycle-consistent image-to-image simulation. We achieve this by training simulator networks to learn how to extract disease pattern and inject or remove to the raw control or disease images. We note that our method can generate both subject level and group level visualization. Specifically, we calculate Jacobian map to visualize volume shrinkage or expansion. And also note that there are some limitations of our work. First, this framework is designed for only control versus one certain disease, which means that it could not handle multi-disease classification classifiers. Second, we didn't combine our results with other a priori regional analysis, so its performance might be doubted. Last but not least, though our framework seems to be independent with deep classifier structure, We didn't conduct experiments to evaluate classifier with other structures such as vision transformer, etc. In the end, I want to note that this is my first author paper, and it's also Qingyu's first last author paper. And therefore, I'm honored that I could have the chance to give a presentation on such a top-tier conference. And I want to thank Kilian for being a great research advisor, and want to thank SN and Qingyu for their kind help. And that's all for my presentation, and feel free to contact me, and I would be happy to answer all questions that is related to this paper. Thank you.